This right here is a Magnavox 8605 console amplifier. It's very small, as you can see, and I bought it off eBay for less than $100 as a fun project. It is a stereo amplifier, and the output tubes are run single-ended. So the original tube complement would have been a 6EU7 tube right here. That is a dual triode similar to the 12AX7 but with a different pinout. And so being a double triode, one triode would have driven each 6BQ5, and that's basically it for the amplifier. It's extremely simple, just a triode right into a single-ended pentode output stage. And then you would have had a 6CA4 rectifier over here. Now, these are very popular amps to buy and mod and, listen to. They're very common, and they can be had pretty cheaply because they are a small, cheap amplifier and they were mass produced. But there is one problem with running these, which is that the 6BQ5 output transformer is designed to drive a 4 ohm load. But most people who have speakers that are high sensitivity for use with tube amps, their speakers are 8 ohms. So that is a problem because it means that you won't be developing the maximum power this thing is supposed to develop, and you'll be having more distortion and such as well. So one solution to this is to simply replace the output transformers, and the Audio Karma user DC Gillespie has a long thread about modding this amplifier, and the solution he advocates is to simply replace the output transformers with modern single-ended 8 ohm ones. Of course, for me, I like to keep my amps as original as possible, and I consider the output transformers to kind of be the heart of the amplifier. So I really don't want to get rid of them and toss them. If I was going to do a build with new transformers, I would probably just do a build from scratch rather than using this thing. So I want to keep these output transformers. And there is a way to do that, which is to run a 12BH7 double triode as the output. And the 12BH7, when both the triode sections are in parallel, coincidentally, it wants about double the load of what a 6BQ5 wants. So that works perfectly with the 4 ohm output transformers. When you hook them up to an 8 ohm load, everything will be about right, and you'll be getting a good amount of power out of those 12BH7s. It also has the benefit of making this into a single-ended triode amplifier, and triodes are obviously good for single-ended because they're very linear and such. So that's what I'm going to do. I'm going to convert this to run a 12BH7 as the output tube, and I'm also going to convert the first tube into a 12AX7 because it's a more common tube, they're easier to get a hold of, and I probably will sell this amplifier at some point, and I want the new user to be able to use whatever 12AX7s they have in their stash. So yeah, so that's what I'm going to do with this amplifier. And we're going to build this amplifier, do the modifications that I mentioned, and then we're going to test it and see how it performs. And while there is a circuit schematic posted by the Audio Karma user FLA Charlie that we'll be looking at in a second, I am going to deviate from that schematic in some ways that I'll discuss in order to obtain better performance from the first stage. So this will involve a little bit of design as well, and I hope it'll be an interesting video. All right, so let's take a quick look here at FLA Charlie's design for the Magnavox 8300 and 8600 12BH7 conversion. So as I said earlier, this is a fairly simple single-ended amplifier, and it won't take us too long to get through everything. So at our input here, we have a 100K ohm potentiometer for volume control, of course, and our 470K ohm grid leak resistor, as well as a 10K carbon comp grid stopper. All pretty standard, but we have something interesting when we get to the cathode of our first tube here, which is, a 6EU7 in the schematic, but could also be a 12AX7 or whatever. And that is this 150K ohm resistor that connects the B plus to our cathode. Now, what's going on here is basically as follows. This 150K ohm resistor forms a resistive voltage divider with our 820 ohm resistor. And so you can see that's actually feeding a little bit of positive voltage from our B plus to our cathode. Now, why would you do that? Well, the reason is that the cathode bias resistor right here, it produces degeneration because the current that flows through the tube is flowing through this resistor. That causes negative feedback, which reduces the gain of the tube. And at this amplifier, gain is in a premium because you only have one gain stage before the output stage. So you really want to preserve all the gain you can. And And feeding some positive voltage from the B plus to the cathode allows you to make this resistor smaller. You need less resistance there to reach your desired positive voltage. Of course, without this resistor, you'd be relying purely on the quiescent current flow through this resistor here. And if you do the math, you can see that 820 ohms is not enough to produce 1.34 volts. So you'd have to raise the value of this resistor, and that would give you more degeneration. So this is a really kind of ingenious way to preserve some gain in this amplifier. And of course, you really need all the gain you can get with such a simple design. Well, what's the drawback of this? Of course, nothing in life comes for free. So there is a drawback of this, and there's a reason this isn't employed on a lot of amplifiers, and that is you can see that whatever ripple and hum and other nasty noise is on your B plus here, now you're feeding it to the cathode. And the cathode of a tube is a non-inverting input. So whatever you put on here is actually in phase with the output. And as a result, you're kind of amplifying whatever noise and stuff you get on here, and it adds to whatever noise you have naturally on your in your plate supply. So you're actually increasing the noise and the ripple and whatnot of the stage by feeding your B plus to the cathode. So I'm going to do away with this arrangement for that reason and another reason, but just to explain to you, that is why we have a 150K resistor here, kind of a weird resistor. And I think that, the gain of this amplifier is low enough that this probably isn't a big deal, but I do have a new solution for it to avoid that issue. And then, of course, here also in our cathode, we have our negative feedback getting fed in here, 6.8K resistor to set the level of the feedback, and a capacitor for the step network and the compensation of the negative feedback. And of course, the reason we can't run this resistor fully bypassed is because then our cathode would be at AC ground, and we couldn't have negative feedback developed across the cathode. So that is why you cannot fully bypass this, and they've had to go for this interesting arrangement here. So for our plate load resistor, we have 470K, coupling cap, and then 470K for the grid leak for the output stage. So these, of course, these two resistors form the load, the majority of the load for our first stage. So it's about 235K plus the Miller capacitance of our output stage, of course. And then for our output stage, really nothing remarkable here. Simple parallel triode output stage with a cathode bias resistor and a bypass capacitor. And the 11.5 volts of bias here will give us about 6 watts of plate dissipation. Our maximum for the whole tube with the two halves in parallel is 7 watts. So this is running pretty damn close to our maximum of 7. But, the 12 BH7s aren't hugely expensive, and in a single-ended amp like this, you're not making a lot of power, so it is kind of useful to get all that you can squeeze out of this thing. And our output transformer, nothing to remark at, simple single-ended output transformer. Yeah. Power supply, also very simple, nothing really to say here. We have our simple resistors for decoupling, and our capacitors here. Now, the main gripe I have with this design is not with the input stage, is not with the output stage. The output stage is, as far as I can tell, is pretty much optimized. I mean, aside from making major modifications to the amp and converting it to fixed bias or something like that, this is the best operating point you can do, no doubt about it. So I'm keeping this output stage exactly as it is here. But I'm not a huge fan of the way the input stage is configured. As I mentioned, there's the issue with the B plus ripple and noise getting fed to the cathode through this, through this resistive divider arrangement that I discussed earlier. But there's another problem with this input stage, in my opinion, and that is the low B plus voltage. You really, I think, for optimum performance, you want your B plus of the input stage to be as close to the general amplifier B plus as possible. The amplifier already has a very low B plus. It's only 280 volts, and this stage is resistively loaded, so you're basically having it again. So I really would like to have this B plus be higher. And I'll show you in a second. I'll show you on the load line that it is beneficial for distortion, both for our overall distortion and for our ratio of second to third harmonic. It's beneficial to run this at a higher plate voltage, and so yeah. So one of the reasons our plate voltage here is so low, of course, we have a 470K ohm resistor for our plate load, which I'm not going to change, but that is part of it. But we also have our 20K ohm decoupling resistor in the power supply. And in addition to the current that's drawn by the actual tube itself, we have the current that's drawn by this resistive voltage divider through here. And so as a result, we are dissipating more power across this resistor than we really need to be. And so by eliminating this voltage divider here at the cathode of our tube and by reducing the value of this, we'll be able to get our B plus voltage much closer to 280 volts. That'll get our plate voltage up and will increase the performance of this first stage. So that's what I'm going to show you in a second. Let's take a look at the load lines and also at my new schematic for this amplifier. All right, so quickly let's take a look at the load lines to see why it's beneficial to raise the B plus voltage of the first stage and kind of reconfigure it. So here, this load line is basically what FLA Charlie's schematic would give you. As you can remember from that schematic, we had 1.34 volts on the cathode, so that's our grid bias voltage here. And we also had a voltage from the power supply of about 215 volts into this first stage. And yeah, with 40 volts of output headroom, the calculator is giving us about 4% second harmonic distortion and 0.87% third harmonic distortion. Now, if we go to a higher B plus voltage and a higher idle current, you can see that with the same output headroom, our distortion is now only 1% for second and 0.57% for third. That's down from 4% and 0.87%. So as you can see, we've lowered our distortion significantly here by raising the B plus voltage and raising the idle current. So that is why I'm going to be making those changes so that we can get a higher voltage here for the first stage of our amplifier. So now let's take a look at my 12BH7 schematic based on the changes that I proposed a bit earlier to the first stage especially. And I'm going to focus on the differences, of course, because in reality it is quite similar overall. So starting with our first grid stopper, I did lower the value of this to 4.7K from 10K. This puts our cutoff point at more like 200 kilohertz as opposed to 100, which obviously doesn't really matter, but I don't know. I thought reducing the value of this might be good. I also have 4.7K resistors that I want to use for this, and 200 kilohertz is more than sufficient for this, I think. So anyways, then coming to the cathode, this is where most of the changes have been made. So in place of the old arrangement, what I have here is a partially bypassed cathode. So this is a concept that I saw at use on the Heathkit A8A that I recently restored, and I wanted to give it a spin myself. Basically what this does is it preserves our gain in a similar way to the previous design of this, except now we are using cathode bias resistors to develop our whole bias voltage. But instead of having one, we have two. And so the majority of the resistance is actually bypassed. So we're not going to be getting any degeneration from this. The 2.7K, which is the bulk of the resistance, is bypassed by this 20 microfarad capacitor. Only 100 ohms is unbypassed. And the reason we need this unbypassed portion is, of course, because we need to have this be the lower leg of our voltage divider for our negative feedback. If this wasn't here, then we wouldn't be able to develop any negative feedback voltage across on the cathode. So this forms the potential divider for our negative feedback, and that's why this can't be bypassed. But anyways, yeah, we still have our negative feedback components here. I haven't inputted any values for them yet because I want to determine the negative feedback resistor value and step network capacitor value based on experimentation and based on measuring the open loop gain. I don't think FLA Charlie actually did a mathematical calculation for this. I think they just ballparked values based on what other people have done, which is totally fine, but I want to go about this in a methodical way and determine what these should be based on testing to make sure we're really using all of the output power of this amplifier. and getting the best square wave response that we can out of this thing. So yeah, otherwise, I did add a grid stopper for our output tubes. Of course, just always a good idea in my opinion, and it won't really hurt any performance of the stage. And then the last difference is in the power supply. I did reduce the value of this decoupling resistor to 10K from 20K, and I am using a different CAN capacitor as well. Mine is a 40-40-40-40. So we have one section here, two sections here, and one section here. And that does fit in the same capacitor mounting position as the original CAN capacitor did. So yeah, that's basically it for the design. Overall, very similar, but I did redo the first stage, and I think that the removing the current draw of the potential divider for the cathode and reducing the value of the decoupling resistor should give us closer to 260 volts of B+, which I think will increase the performance of this first stage. So without any further ado, let's get straight into building and see how this thing performs. All right, so now that we've taken a look at the schematic and we know what we're going to be doing with this amplifier, it's time for the next step, which is going to be removing all the old unnecessary resistors, capacitors, and wiring inside the chassis, giving us a blank slate on which to build the new design. So I'm just going to show a time lapse of that real quick, and let's get right into it. All right, so here is the amplifier with the holes drilled. As you can see, I drilled out these two holes on the front for the power switch and the fuse. I also drilled out one hole there for the speaker jack, and then I drilled the hole for our new strain relief. I was having some issues getting that strain relief in, so I did do that off camera, but as you can see, it's all nicely situated and in there. So yeah, now let's get to mounting some of the hardware and setting up our power switches and such. All right, so as you can see, we're getting closer here. We have our fuse, our power switch, and our nice new lamp wired up, as well as our output jacks and our new tube socket in here. So the next thing we're going to do is to get all the wiring in here and start building the amplifier. And the first thing I'm going to tackle is going to be the wiring for the line cord and the power and all that stuff. So I want to get all this stuff here wired up. So yep, I'm gonna have to do some desoldering of some of this stuff and a bit more cleaning up inside here, so let's get to that. Okay, so before we go any further with wiring up the primary side of the power transformer here, I'm going to use a spare heater winding that's on this transformer. It would have been used for the heaters of the tuner that would have been used with this amplifier in a console. But of course we don't have that tuner anymore, and so we have a spare heater winding that is not doing anything. And because these old power transformers typically expect the line to be like 115 to 117 volts, and the modern line voltage is 121, 122, of course, your voltages are all a little high, including the heater voltages. And I don't want the heater voltages to be high because that runs the tubes really hard and causes them to fail prematurely. And so, yeah, let's buck the primary with our spare heater winding. This is a common thing to do, and it helps get your voltages under control back to where they would have originally been with a 117 volt line voltage. So the way to do that is basically to place the unused heater winding in series with the primary of the power transformer. Of course, the phasing matters. If it's one direction, then it'll boost your secondary voltage, and if it's the other direction, it'll reduce it. And of course, we want the reduction. So the easiest way and the simplest surefire way to make sure you have the phasing right is just to test it. So what I've got here is I've got it wired up in one orientation, and we're going to turn this on, take note of the voltage, and then reduce the orientation of that heater winding and see if which one is lower, and whichever one's lower, that'll be our buck configuration, and we'll know how to wire it up. So I've got the amplifier plugged in here. You can't see it, but off screen I do have it plugged in, and I have our wiring set up here, and I have a multimeter hooked to the secondary of our power transformer. So what we're going to do here, I do have this hooked up to a variac, and I have it on a very low voltage, and there's no tubes in there. So we're just going to turn this on and see what voltage we get here on the secondary. Okay, so we have about 25 to 30 volts on the primary now, and we're getting 112 volts on the secondary. So that's a nice easy number to remember, 112. And let's turn this off. Of course, the voltage will very quickly go back to nothing because there are no capacitors or anything in this amplifier right now. So this is very safe to do. And so we are just going to reverse these leads here. Okay, as such. And let's turn this on and see what we get. Okay, 126. So there you have it. The first original configuration was the one that bucks our secondary and bucks our transformer and reduces our secondary voltage. So I'm just going to now wire it up in that configuration, and we'll have a nice bucking winding to reduce our voltages. All right, so as you can see, we've got the primary side of the power transformer wired up with our switch, fuse, and power light, and also the heaters down here and the B+ circuitry as well. So getting close, just got to wire up the grid, cathode, and plate circuits for all of our tubes, and we'll be good to do some testing. All right, so as you can see, the amplifier is pretty much done being assembled. I've wired up all the tube sockets, all the capacitors and resistors and whatnot. The one thing here that I did do that's I had to improvise a little bit is the cathode resistors for our 12AX7s, of course, because I'm doing that partially bypassed cathode resistor arrangement. I needed two resistors at the cathodes, and I didn't want to add like a terminal strip, a tag strip board or anything, so I just kind of wired them up in series with the capacitor bypassing the larger resistor here. And they aren't really attached to anything, but the leads on this capacitor are pretty strong, and since there's three components here, these don't really move around a lot, they're pretty secure, so I'm not too worried about that. Of course, what we're going to do now is test the open loop gain of this amplifier, and we'll use that to do the math to determine our feedback resistor value. Then once we've added the feedback resistors, we can take a look at the square wave response of the amplifier and start to add our step network capacitor if it looks like that's going to be necessary. So yep, let's get right into it and test the open loop gain of this amp. All right, so I've got the amp hooked up and running here, as you can see, feeding it with a nice 120 volt AC input here. And I've got it running, and you can see we've got a nice sine wave on the output. Ignore that jittering around. It's not motorboating, I don't think. I played around with the value of the decoupling resistor, of course, because I was going to decrease that, and sometimes that can lead to motorboating. But I tried both 20K and 10K, and it didn't seem to make a difference. So I'm going to stick with 10K to get higher voltage on the plates of our first input triode. So that's the one thing I did want to test with this amp, was making sure that my lower value decoupling resistor would be adequate, and it looks like it is. So I'm going to just go ahead and install the 10K. But anyways, so the purpose of this is to get our open loop gain. As I said, we don't have any negative feedback hooked up yet because I want to know the gain first before we do that math. So you can see here on the signal generator, we're feeding a 10 millivolt input signal. And on the oscilloscope, we have a 170 millivolt output signal, maybe about 170 to 175. Just go in the middle and we'll say 172 or something. But anyways, relatively similar either way. Yeah, so what we're going to do is take those numbers and plug them into the equations for the negative feedback, and then we'll be able to add the negative feedback resistors and get started on looking at the square wave response and doing any tweaking we might need to do. All right, so now let's calculate the value of our negative feedback resistor, which is the final thing that we need to do with this amplifier before it's done, in addition to the step network capacitor, which we'll do afterwards. And so this equation is something from Aiken Amps, which is a great website. And I'll basically explain to you what's going on here. What this equation does is it allows you to find the value of your negative feedback resistor, which, spoiler alert, is 420 ohms, based on a few things. This negative 100 here, that represents the value of your unbypassed cathode resistor, and I'll show you what I mean here. So remember, we have this unbypassed portion of the cathode resistor, and that's where the negative feedback is going to. So basically, this is the portion of your voltage divider, your negative feedback voltage divider, that goes between the output voltage and ground. I usually call this like the lower leg. I don't know if it has a name, but anyways, if you imagine this is the voltage divider, this is the resistor between ground and the signal output. So that resistor goes into the equation here as a negative value. Then you multiply that by this. And what all this is that the 4 here, this is our desired closed loop gain. So it says after I add the negative feedback, the amplifier will have a gain of 4. And that's not decibels, that's times. So 4 times voltage gain. And this right here is our open loop gain. It's the gain that the amplifier has before negative feedback is added. And that's the gain that we just measured right before, because we had, of course, 10 millivolts input and 170 millivolts output. So the output is 17 times larger than the input. And so you plug those two numbers in, and you plug your lower leg of the negative feedback resistor in here, and you get 423, which would be the value of this resistor right here, the one that's the part of the voltage divider that goes between the output of the amp and the negative feedback, where the negative feedback goes to the cathode. So that's, I call this the upper leg of the voltage divider, because you can see the voltage comes in here, it goes through this, and then the signal output, and then it also goes through this, of course, and the ratio of these two sets of voltage, just voltage divider basics. But anyways, yeah, so that's very simple, and that gives us 420 ohms for our resistor. So let's go and add that resistor and see what happens. All right, so here is the amplifier running with the negative feedback resistors added and our negative feedback implemented. You can see it's those two green resistors right there. I just kind of clipped them in for now. They're not really properly soldered or anything, but it's good enough for testing. And you can see they are working here. We have a very nice sine wave now. It cleaned up a lot of the kind of jitteriness and whatever we were seeing earlier, although I did redo the grounding clips and stuff, so it could be that too. But anyways, you can see that our output voltage now is 140 millivolts. And if I show you the input, it's 45 millivolts. So obviously our gain has dropped quite a bit here. It's actually, now our gain is about 3 times. I predicted it would be 4 when I did the math. I did it for 4 times gain, of course, as you just saw, but it's actually 3 in reality. Again, it's not a big deal because any modern source can typically deliver up to 2 volts, and so we really don't need that much gain at all when this amplifier is only going to be outputting, 3.5 volts. So this should be more than sufficient as far as the gain goes. And so I'm quite happy with this. It'll give us a lot of negative feedback to really give us the best performance we can get from this amplifier. And so real quick, what I'm going to do next is, of course, the last step once I solder these resistors in is going to be doing whatever compensation we need to get our square wave looking as best it can. And I'll just show you right now that our square wave could look a little bit better. So let's go to square. You can see there is a bit of ringing on the leading edge of our square wave. And I'm going to zoom in here, and I'm going to increase the frequency, and you'll see you'll see that, so we still have, this is at 10 kilohertz. You can see that we do have a bit of ringing on that leading edge. It's definitely not bad, and this is a lot of negative feedback for this amplifier, actually, in my opinion. Just a cheap little single-ended amplifier. These transformers are probably nothing to write home about. So I'm pretty impressed with that square wave response, especially with so much negative feedback. But we are going to be adding a step network capacitor across our negative feedback resistor once I get those soldered in, and we'll see what we can do with this square wave. All right, so I've got the amp running again here. This time the negative feedback resistors are properly soldered in there, and I've also I've soldered them to this tag board right here, the tag strip, and then I've run wires to where those cathode resistor junctions are. So yep, got that all configured, and then I've wired a capacitor in here across the negative feedback resistor. And that's what's called a step network, and it changes the frequency response of the negative feedback and helps you to get your negative feedback square wave looking nice without any ringing and whatnot. So this is a 4700 picofarad capacitor, and it's smoothing out the high frequencies on the amplifier, as you can see. So the yellow channel, the yellow trace on the oscilloscope, that is the channel with the 4700 picofarad capacitor for compensation. And the blue trace is the one without the capacitor. And as you can see, the blue trace has a significant bump at the front of that square wave. It's actually not ringing, which is nice, but it is a bit of a high frequency boost there. And adding the capacitor across that negative feedback resistor just tones that boost down a little bit and gets our amplifier a little bit better behaved. I think either of these square waves would be totally satisfactory, especially since this is a 10 kilohertz square wave, which is pretty high in frequency. So already, this is already approaching the edge of what we reproduce for audio frequencies. So to have the square wave be looking this good is quite impressive. But of course, always want things to be as good as possible. So nice to kind of get rid of a little bit of that hump on the leading edge of the square wave by using that 4700 picofarad capacitor. So I'm just going to wire 2 of those, 1 for each channel, and that'll be the end of the work on this amp. I think it's pretty much done. It seems to be performing really well. So after that, we'll take our final distortion, frequency response, etc. Performance tests, and that'll be it for this video. All right, so I finished assembling the amplifier. I put the 4700 picofarad step network capacitors across the negative feedback resistors, and I've been listening to it and testing it, and I'm really happy with how it performs. So let's get right into the measurements here. And for starters, we have a frequency response sweep. Um, Ignore the scale here at the left in SPL. I measured the output level, and I know that the flat part of the frequency response is half a watt into 8 ohms. So anyways, at the high frequency end here, it's very nice and well controlled. We're flat all the way out to 20 kilohertz approximately, and then it starts to nicely roll off after 20 kilohertz. So very happy with how this turned out, and our high frequency stability and everything seems to be really great with this amplifier. At the low frequency end, you can see we do have a bit of a roll off here, beginning at 60 to 70 hertz. Not too surprising. This thing has very small output transformers, and the console that this amplifier would have been used in originally would not really reproduce super low frequencies, so it's not surprising that this rolls off here. But anyways, very happy with how this frequency response turned out overall. And let's go on to the distortion spectrum next. So here we have 1/10 of a watt. And normally, you test an amplifier at something like 1 watt, 5 watts, 10 watts, 20 watts, whatever. Of course, in this case, the amplifier doesn't do more than 1 watt, really. So I chose different power levels. I chose 1/10 of a watt, half a watt, and 1 watt. So anyways, here is the 1/10 of a watt result, and I did it for both channels. So the variation in between these two graphs that you see here is a result of the tubes, and I verified that by swapping the tubes between the two channels, and the performance changes based on which tube is in which channel and not the actual channel itself. So this is a tube effect of my output tubes just being slightly different in terms of how they perform, which is pretty normal for a single-ended amplifier, especially one with relatively low feedback. The ultimate amount of feedback in this amplifier ended up being about 14 decibels of negative feedback, which is, not a super low amount, but some amplifiers will be running more like 20 decibels if you have a really high performance hi-fi amplifier like a Williamson or something of that nature. So anyways, yeah, slight variation between our two tubes here, but nothing super surprising. Our distortion level overall at this 1/10 of a watt power level is something like negative 50 decibels, as you can see, and it is dominated by second harmonic, which is kind of what you'd expect for a single-ended amplifier at this sort of this is a comfortable power level for this amplifier, I would say, and you have mostly second, a little bit of third, and not a lot of higher order harmonics here. And then at the noise on the left hand of our graph, I'm very happy with how the noise levels turned out in this amplifier. 60 hertz noise, as you can see, is very, very low, which I'm very pleased about because, obviously there are limitations to the heater wiring in this amplifier. The chassis is pretty small and cramped, and, and I'm having to wire the heaters across the socket because we're using a 6.3 volt heater winding for the 12 volt tubes. Also, I ran a lot of the grounds through the chassis because that's how this amplifier was originally configured, and I didn't want to, make too many modifications to it. I wanted it to kind of look underneath and be constructed similar to the original. So I did clean up some of the grounding relative to how the original amplifier had it, and I consolidated some of the grounds together, but I still did use the chassis to, run to unite all of our grounds. And so I'm happy that despite that, our 60 hertz noise level is quite low here. Also, our 120 hertz noise level is very low as well. And that's nice because this amplifier doesn't have a choke in the power supply. It only has a decoupling resistor. Well, multiple decoupling resistors. But for the main B+, we only have that 50 ohm decoupling resistor, and yet our hum levels here are very low. Also, because it's a single-ended amplifier, we don't get the common mode noise rejection of a push-pull design. So despite the fact that despite all those factors, our noise levels here are very, very low, I'm very pleased with that. So anyways, let's go on to the next power level, which is half a watt. So here we have the half a watt results. Again, there's slight variation between the two tubes, and as you can see, at half a watt, our higher order harmonics are beginning to, kick up here a little bit, which isn't ideal, but, half a watt is already kind of approaching what this amplifier is capable of outputting, so we're getting a little bit of higher order harmonics starting there. But yeah, our performance here about negative 43 decibels of THD. And so yeah, nothing too much more to say there. And yeah, once we get to our 1 watt results, you can see here the higher order harmonics really do start to pick up at 1 watt. Um, and yeah, so the actual THD level isn't much higher than half a watt because the main increase is in the higher order harmonics and not the second, and the second was previously dominating at those lower power levels, but now our higher order harmonics are almost caught up with the second. But anyways, overall, very happy with how this amplifier turned out. I think these performance results are about the best that you can expect from a super low power amplifier that is single-ended and uses a preamp tube as or a driver tube as the output tube. So very happy with how this turned out, with the amount of negative feedback we managed to get into this thing and the fact that it's still very stable despite that. So I'm just going to show a picture of what the finished amplifier looks like while it's running here, because you've mostly been looking at the bottom of it and not the top. But I think it looks really nice. It's a great compact little kind of desktop amplifier, and it works really well with sensitive horn type speakers. Of course, with distortion rising quite a bit as you approach 1 watt in power, this is really an ideal amplifier for use with very sensitive speakers, and I do have nice all-tech horn speakers that I've been listening to this with, and it sounds great with those. Obviously, with lower sensitivity speakers, you're going to be, not having a lot of volume out of this thing. But anyways, yeah, so I'm going to post the full resolution schematic on my website, as well as the full resolution versions of all the performance graphs that I made. And so, yeah, I did make some changes between the schematic that I showed earlier in the video and the ultimate schematic that I ended up using. Of course, I added all the negative feedback component values that we determined, and I also eliminated the grid stoppers of the 12BH7s. I just figured they weren't really necessary, and they would have required some additional effort in wiring because I don't know where I would have put them and connected them. So I removed those just for convenience, and it doesn't seem like that's had any ill effect on the amplifier. So yeah, that's another difference. So you can see the final revision of the schematic if you click on the link in the description. And if you end up building this amplifier or modifying a Magnavox console amp 8600 or 8300 series to use my schematic, please let me know how it turns out and how you like it. I think this is a really fun, easy, simple build that anyone can do if you have a good amount of experience working with tube amps, and it's not a time-consuming build, and there's not a lot of parts that you have to purchase to do one of these. So really happy with how this turned out as a fun little project for a low-power desktop single-ended Triode amp. And yeah, if you have any thoughts or any questions or feedback, please leave a comment below. And thanks for watching.